We're going to start off talking about equations in two unknowns though, so just linear simultaneous equations in terms of x and y. Graphically, these are the three options that you can have for these straight lines. So most of the time, if you've got two straight lines in two dimensions, they will meet at a single point, and we'll say that's one unique solution. In this case, when you're setting up the matrix equation to solve this, this means that you can solve this, and it means that the determinant of that matrix isn't zero. Okay, so if you work out the determinant of your matrix and you don't get zero, that means that your lines do cross somewhere and there is one unique solution. The other options are you have parallel lines, in which case you would get that the determinant of your matrix is zero. Okay, so that also in itself has two options. Either the lines are parallel and don't meet anywhere, like the second one here, in which case the determinant matrix is zero. But also you could have that the two lines are exactly the same thing and they cross each other and they have infinitely many solutions. All of the points on this line work with infinitely many solutions, which also has the fact that the determinant is zero. So because both of these have the same determinant of zero, once you found the determinant of zero, you have to do a little bit more work. It isn't just that because the determinant is zero, you get no solutions. If you get the determinant of zero, it's either no solutions or infinitely many solutions. In which case, then you need to look at your equations of the straight lines, and either they'll be the same equation or they will be like a multiple but equal to something different. Okay, so you just have to look at them. There's a little flow chart here, but I don't know how to spell that. So just a quick example on this one. So this example here, we've got a pair of linear simultaneous equations, which we're going to turn into a matrix equation first. So remember, you write the coefficients of your x and y's as the element in your matrix. Times this by x, y. This is equal to the answers in a vector, so equal to 8. First thing to do is to calculate the determinant of this matrix. So the determinant of this matrix is 3 times 4 times 3 times 6, which shockingly you get 0, which means that either there are no solutions or there are infinitely many solutions. And to work out which is which, we have a look at these. So either you can simplify each thing down and show that you get the same thing, or you can say that the second one, if you times it by 1.5, you'll get the first one. Either's fine. So equation 1, if I divide all of that through by 3, I get x plus 2y equals 6. Equation 2, if I divide all of that by 2, I also get x plus 2y equals 6. Therefore, they're infinitely many solutions because these are the same. How about doing the same thing for the question for you? Pop the answer in the middle. So, okay, answer for this one. So if you work out the determinants, you get 0 for the determinant. So either they've got no solutions or infinite solutions. I would have times the top one by 3 to make them look the same. So you get 3x plus 9y equals 9 for the top one. They look the same, but they're equal to different things. So one's equal to 9, one's equal to 8. You can say that those equations are inconsistent, which means they're no solutions. They're two parallel lines that don't cross. Just like how we started with 2 by 2 matrices and went on to 3 by 2 matrices, same thing here. We started with 2 unknowns and now we're on 3. It's more complicated, obviously, when you get into 3 unknowns, but the basic idea is the same. You've got 3 sets of simultaneous equations in 3 unknowns. You can obviously turn this into a matrix equation from 3 by 3 matrix. And same thing again, you start out by working out the determinant of this matrix and see whether it's 0 or not. If it's not 0, then that means that you can solve this and there is a unique solution. Okay, so again, if the determinant of your matrix is not 0, that just means there is a unique solution. Geometrically, this means that you have 3 planes meeting at a point. So a plane in 3 dimensions is just a flat surface. Okay, this ax plus by plus c equals something is an equation of a plane, which you will need in the vectors to find. Okay, so these are three equations of three planes, three flat surfaces. You can imagine, like, if you think about this room, so like this wall, the wall with the windows on, the floor there, that's like three planes. Okay? And if they meet at a single point, that's the corner of the room. Okay, so that's if your determinant is not equal to 0, you do get one unique solution. The tricky thing is what happens if you don't get, or if you do get 0 for your determinant. Just like for the straight lines in 2D, you've either got infinitely many solutions or no solutions, but there are more options for what it could be in 3D. Okay. But basically, you're looking for the same thing. So you're looking, once you've got the determinant at 0, you're looking at your three equations and seeing if any of them are multiples of each other, if any of them are the same thing. So if you do get the determinant of the matrix of 0, have a look and see if any of them are multiples of each other. If all three of them are the same, which is very rare, but if all three of them can be turned into the same thing, this is three equivalent planes that all overlap and there are infinitely many solutions. That one's rare. If you've got instead ones that are not all the same, what you then need to do is start solving them by hand. So remember last lesson, we started solving them by hand by eliminating z usually, and then you get x and y. If you do that and you end up with consistent equations, so equations that do work, and you will get down to like with x and y that will be the same or something like that. This means that your planes do cross each other all together along a straight line. And we say this forms a sheaf. It's like a book opening on all the pages. So that we say that forms a sheaf. Okay, so this is one of your options for infinitely many solutions. Basically, if you get consistent, if you get consistent equations, there's infinitely many solutions and they form a sheaf. Alternatively, if you get the determinant m equals 0 and you get inconsistent equations, these are what options you can have. So these are your no solutions options. So if you look at your equations and all of the like x, y, and z are the same, but they're all equal to different numbers, this is three parallel planes that don't cross each other. You might get that two of them are the same but equal to different numbers and the other one's a different one. This will be two parallel planes which also don't cross each other and they'd cross the other plane. That. Or if you try and solve your equations and you get inconsistent equations at the end, you get three planes that are not parallel but don't meet each other along the middle line. We say they form a prism. So in the middle of here, there's a triangular prism. They'll never all cross each other at the same time. It's a lot to take in at once. It will take a while to wrap your head around. And like I said, I think it'll make more sense once you've done the vectors.
Yes, but do we have to remember the names of them?
Well, the other ones you need to remember the name of a sheaf and prism, but yeah. Okay. There's a massive flow chart here. It's up to you if you find it useful. I'm not going to go through it. Let's have a look at some examples and hopefully this will make a little bit more sense. So for each of these, I'm looking at how many solutions and what's happening geometrically with these. So I'm going to set these up as matrix equations first. Got 3, 2, minus 4, 2, 0, 1, 1, 2, 3. This matrix, notice that y is missing from the second equation. Times by x, y, and z. First thing I'm going to do is the determinant of that matrix. So determinant, let's call it M. I'm going to pick the middle row to do the determinant on, or you can do the middle column, or you can do anything, but just because it's got a 0 in it. So if I do the middle row, cross out the row that 2 is in, cross out the column that 2 is in, and do 2 times the remaining determinant. Notice that I've made it minus because of the plus minus pattern as well. It's in a minus position, so I've made that one minus. plus 0 in the middle, and then minus 1 times the determinant. It's minor. So cross out the row that 1 is in, cross out the column that 1 is in, and that's times 3, 2, 2. And again, notice I've made that one minus because again it's in a minus position. Plus minus plus minus. If you prefer, you can always use the top row and then you don't really have to worry about that. Work out this determinant, so that's minus 2 times 6 minus 2, and minus 1 times 6 2. That gives 3 minus 16 minus 12 and minus 20. Because I haven't got 0 for this determinant, that means there is a unique solution. To the system of equations. And geometrically, this is 3 planes meeting at a single point. Okay. Do the same for the rest of the planes. So again, set this up as a matrix equation. 1, 2, 3, 2. Z. I'll do the same for this one. This time we're going to choose the first column, so it's got 1, 1, 0 in it. Start with the first one, cross out the row and column that it's in, and times it by the it's minor. Minus 1 times that one. Minor. Remember, it's in a minus position there, so rather than plus minus pattern, so that needs to be minus. Row and column that 1 is in. And we've got 2, 3, 1, 2. And then final one I don't need to do because I chose it so that it was a 0. I don't need to work that one. This gives me 1 times minus 1 minus 1 times 4 minus 3. We're just going to give it 0 this time for the determinant. So there's not a unique solution this time, but just because I get the determinant is 0 doesn't mean that there's no solutions. It means that if there's no solutions, or there's infinitely many solutions. So I need to do a little bit more work on this. So this is where I now go to start solving these equations by hand. So I call them equations 1, 2, and 3. First thing to do is to have a look at these and see if any of them are multiples of each other, if any of these are parallel planes, which they're not. Okay, so there's no x in the bottom one, but obviously these ones have got x's in, and these have both got the same x, but there's 2 y and y, so they're not multiples of each other, they're not parallel. So either I'm going to solve these equations and it's going to work, it's going to be consistent, so they're going to form a sheaf, or I'm going to solve these equations and it's not going to work, they're going to be inconsistent and they're going to form a prism. Okay, those are the 2 options because there's no parallel. I'm going to eliminate x from these ones because it's the same, it's easy. So I'm going to do equation 1 minus equation 2. So x's will cancel out. 2y minus y gives me y. 3z minus z gives me 2z. And 3 minus 2 gives me 1. This is the same as equation 3, so you can say that these equations are consistent because I've got the same thing. They're consistent. If they're consistent, it means infinitely many solutions. Infinite solutions. And if you think about infinite solutions, it means your planes must all cross at some point. There's no parallel planes, so the only option is that they all meet along a single line. So for 3 planes. Form a sheet. Last one on here. Let's set this up with the matrix again. We'll talk about 1 minus 3, 1, 2 minus 7, times x y z equals 3. Again, do the determinant of this one. So there's no zeros in here, so you can just choose any. So I'll just choose the top row to do the determinant. So for 1, cross out the row and column that it's in, and do the determinant of the remaining numbers. Then minus 3 times it's minus, so cross out the row and column. And the determinant of 1, 1, 2, 8. And then plus 3. And it's minor. Cross out the row and column. Get 1 minus 2 minus 1 minus 7. Calculate this. So 1 times minus 16 minus 7. Minus 3 makes a plus. Times 18 minus 2. 3 times minus 6 minus 2. You do get the determinant in 0. Again, it doesn't just mean there's no solutions, either there's no solutions or infinitely many solutions. So again, we have to start solving these by hand. So you can eliminate whichever letter you want. I'm going to eliminate x again because I think it's the easiest one to do. If I just do equation 2 minus equation 1 or 1 minus 2. Just gone for 2 minus 1 because 4 is bigger than 3. I'll eliminate x from that one. So minus 2y minus 3y gives me positive y. Z minus 3 z gives me minus 2z. And 4 minus 3 gives me. I now need to eliminate x a different way. So if I do equation 3 minus 2 times equation 1, I'll do the way around. So I get 2x minus 2x, that cancels. Minus 7y minus 6y will give me minus y. 8z minus 6z will give me 2z. And 4 minus 6 from the first one will be minus 2. Obviously, I could change the signs to make this one match the first one. So y minus 2z. 2. So you get the same thing on the left-hand side for these, but they're equal to different things. So these equations are inconsistent. So there are no solutions to this. So they're consistent, there's infinite solutions. They're inconsistent, there's no solution. Geometrically, have a look at these and see if any of these are multiples of each other. Well, they're not. So if you doubled any of these to get 2x, they're not the same as the final one. Obviously, these have got the same x, but none of the rest is the same. So these are not parallel equations. So it's not that all 3 are parallel. It's not that 2 are parallel. It must be that these form a prism. Geometrically. lines. All of them. They don't cross each other all at the same time. So this one's got some A's and B's in it and stuff. It wants us to work out what values of A and B the equations will have unique solution, non-unique solution, and no solution. Set this up with the matrix equation first. So 2 minus 1, 2, 3, 4, 5, 9 times x, y, z. 6. B, make sure your B looks different to a 6. And looks better. First thing I'm going to do is the determinant of this matrix here. We'll call it matrix M. Again, doesn't matter which row or column, so we'll use the top row. So 2 times its minor. The determinant of 1 minus 4, A minus 9. Then a minus, and it's minus minus 1 times its minor, which is 3 minus 4, 4 minus 9. And then plus minus 1 times its minor, which is 3, 1, 4. Okay. Work this out, we'll get a determinant in terms of A. 2 times minus 9 minus minus 4A. 1 times minus 27 minus minus 16. Minus 1 times 3A minus 4. Balance out minus 18 plus 8A. Minus 27 plus 16 gives me minus 11. And minus 3A plus 4. Tidy this up so I get 5A and minus 20. So this is the determinant of M in terms of A. So for there to be a unique solution, all it has to be is that this determinant has to not be equal to 0. Okay. You add 25 divided by 5. This just means that for there to be a unique solution, A cannot be 5. And it doesn't matter what the value of B for this is. As long as A is not 5, I can do the inverse of that matrix and I will get a unique solution. So most of the time you'll get a unique solution.
That will specify if it's a real number.
It'll usually specify it in the question. Then for both non-unique and no solution, so non-unique means infinite. It has to be determinant as 0. So both of these will be A equals 5. And then we need to work out what's happening with B. So if I write down these equations with A is 5 in, so we've got 2x minus 3.
Plus 5 plus 5.
Okay, so these are my equations now that I've got A equals 5. So I need to work out the consistency of these. This time I'm going to eliminate Y because there's minus Y and plus Y in here, so you can choose any one. If I add equations 1 and 2, I'll eliminate Y. So I get 5x minus 5z. 5, which obviously I can write as x minus z equals 1.
It's I think about it.
Then to eliminate Y a different way, so I'm going to times equation 1 by 5 and then add it onto equation 3 to get rid of Y that way. 5 times equation will give me 10x plus 4x and 14x. I'll get minus 5y plus 5y cancels out. Minus 5z minus 9z gives me minus 14z. And then 6 times 5 is 30 plus 40.
Find some Wednesday.
The left-hand side is obviously I can write the same. To make it a little bit less awkward, I'm going to times this one by 14. The right is 14x minus 14z. You could obviously divide this one by 14 and it will be fine. So these are consistent when 30 plus b is equal to 14. If I minus the 30 across, these are consistent when b is equal to minus 16. So there are infinite solutions when b equals minus 16 and a equals 5. And there are no solutions when b is not equal to minus 16 and a is equal